Welcome everybody to the Killer Interface talk from Jerre here at Vlog. Nice to see you all being here and joining. Let me introduce you to Jerre shortly. It's a colleague of mine working at Vlog. Let's do some killer interfacing.
Yeah, thanks, Tobias. Tobias was actually a member in my team, a current client I'm working for. So we know each other indeed. And I want to talk to you all about killer interface patterns for consistent API design. So I will be sharing this screen, if that works.
Yep, beautiful.
Yeah, so that's no weird boxes or anything around it. Okay, then let's get started. So indeed, I want to talk about these interfaces that is a square in the middle of the screen here, and what we can do with it. But of course, this wouldn't be a talk, IT talk, if we didn't have a disclaimer, because what I'm about to tell you is, of course, opinionated. I should say it worked indeed, and still works great for us, but it might not be the case for you. And as always in IT, if you ask the question, should I use this, or is this something that is indeed that works great? As always, the answer is it depends. So of course, consider that as well. Now I want to start with something that is not in IT, and this is a picture of a bar magnet, actually. A bar magnet that has a North Pole and a South Pole. And I always wondered, okay, when does a North Pole turn into a South Pole? Is that how does that work from high school maybe on, or maybe even a little bit earlier? And of course, you could say that maybe there is an interface between the North and the South Pole. But then, of course, you could do a little experiment and ask yourself the question, but what if I cut this bar magnet in half? Now, we know the answer because you can actually do that experiment. And when you do that, then you actually get two bar magnets with a North Pole, a South Pole, a North Pole, and a South Pole. And you can separate the two. And even if you look at pictures where they have maybe thrown some iron dust around it, then you would actually see the magnetic field lines between the North and the South Pole. And this actually is a concept or an analogy that I would like to use in the back of my mind when I'm thinking about IT products as well. For instance, about applications that you might have started to build as a hobby, or maybe as a small team at the client, or maybe even at your own company. So when you're considering an application or a system or a monolith, then what would happen if you would cut this into multiple pieces? Now, of course, this pattern of cutting up your application into more smaller application is, of course, where most of us are heading towards a microservice architecture. But will it work the same way as with the bar magnet? Now, of course, as always in IT, it depends. If you have a monolith that is basically a big ball of mud, then when you are going towards a microservice architecture, you would just end up with a distributed ball of mud and not really a nice microservice architecture. So just like the bar magnet that is built out of molecules and smaller bar magnets, if you will, your application should also be nicely built up out of modules. When your system is actually built out of modules, then of course you could potentially scale out maybe this C module or this D module if you cannot scale up your monolith anymore, because you can put so much memory or so much faster CPUs that at some point you cannot do that anymore. So if you want to still be able to grow your team, your organization, and your application, you might want to consider that and actually go towards a microservices architecture. But of course, the patterns that you would have in this monolith, for instance, making these classes that implement interfaces and all this nice object-oriented programming patterns, you might lose if you actually go to a microservices architecture. So in this case, when you have your front end or North Pole here, or your back end or your South Pole here, you might be able to split it up into multiple bar magnets because you have nicely modularized your monolith. But when you do this, then of course you're not inside your language of choice anymore. Not maybe you had your monolith in Java, and now you cannot take or import interfaces from one part and implement it in the other part. So you're losing something. And this talk is actually about how might we get some of that back and put it into our microservices architecture. And for that, of course, we need to also look at interfaces and what interfaces are. And for that, of course, you can have another analogy from outside of IT, and that is when you are thinking about air and water. Now, you can speak about an interface between air and water. It's right here. It is actually where air and water come together. So if you look at this, questions like where does the interface begin and where does the interface end doesn't really make sense. So an interface is actually where the water and the air meet. And an interface does not exist in the water or in the air. It's where these two things meet. And actually, when I looked at Wikipedia to find the definition or a definition of an interface in computer sciences, actually that is really nicely well reflected, because an interface is indeed a shared boundary across which two or more separate components of a computer system exchange information. So I would like to use this definition as an interface here as well. So when we're talking about killer interface patterns, these are regarding interfaces that indeed are between separate components. And indeed also to exchange information. So let's consider one of these services. And let's think of this service as a pipe. And this service actually takes in some data and puts it towards the backend, or maybe even takes something from that backend and presents it to the front end. Now, this can indeed be a service like we are used to in a microservices landscape, where on this side we expose a RESTful API and we model that in a controller, for instance. If you're familiar with your Spring Boot applications, where traditionally you would set up a controller, a service, and an adapter, then your RESTful interface would be modeled by the controller. Your business logic would be implemented by a service, and you would connect to other services or databases with maybe an ORM client or an HTTP client or adapter or something else. And you would do some logic there. But of course, the pattern from just your plain old object-oriented programming could be that on this side, you would just implement an interface, a Java interface, for instance. Your class is then the implementation, and then maybe you program to another interface to get some data out of another system. So in this way, you could think of these OOP principles in the same way, maybe. So let's go to our first pattern, a service-to-service interface, and how we might be able to leverage interface definitions on both sides of an interface in a microservices architecture. So if we are indeed are concerned with this RESTful API, maybe we want to define it as an interface outside of our actual microservice. And of course, we can do that. For instance, in a project, you could define a user API separately from your user service. And ideally, you could maybe even define the user API in a different repository than your implementing service. Now, when you do that, you can just define your abstract APIs, in this case in Java, like this, as a user API, and maybe there are some other objects that you need because you are indeed communicating across an API with your upstream services. So in this case, you could define them as interfaces as well. Now, an example of a Java interface is this, where if you know Spring, you might already also notice these annotations. So in this way, you can define as an interface a user API with, in this case, three methods. A method where you can get users that returns a list of users, and maybe get the user by name, and maybe save some data from a front end, from an upstream service that then returns again some other user. And if you don't know Spring, these annotations just tell you that the request is mapped to a path, in this case /API, and this is a get HTTP method, and here as well, but then by name, because this will be appended to this API, and of course also a HTTP post. Now, if you also annotate this with Swagger annotations, then you can actually also generate documentation from this API, and we will use that. Later. Now, an API is indeed an abstract interface or an abstract thing that actually is used to communicate data. So if we want to model that data as well, we can use a public interface as well that models our user, our data. So in this case, it would be get name, get birthday, and maybe some metadata or something else that you want to model. And this would then indeed be another interface that you can model. Now, as you might notice, if you annotate this with value mutable in the case of Java, then that is a library that takes this interface and actually generates a immutable implementation of this user using this interface. And we can leverage that later. Now, if we also annotate this with Swagger annotations, we can actually reflect that this property is required in the Swagger JSON like this. And we need to be able to annotate this with nullable, that the value immutable indeed knows that this is not a required property. And with this, you actually have all the basics set for our first pattern. Because if you then generate the immutable objects and a Swagger documentation, you can then start using that. So then in your service, in your typical Spring Boot pattern of a user controller, maybe repository and service, you can then start building your controller. Now, a typical controller might look like this. You might recognize these annotations again, a request mapping from API, a get mapping by name, and a post mapping. This is now, by the way, in Kotlin, but that's for later. And then you could just implement some code to actually find a list of users in a service and then return it. But this is not yet leveraging the fact that you just defined an API. Now, if you then indeed implemented API, so for instance, this is the user API that we've just defined in Java, then of course you get a huge benefit, because now you are actually implementing an API that you yourself might not have defined, or maybe you have defined, but this is something that that is already defined and you already have documentation for. Normally, I think most people would just write code first and then documentation later, and that's why documentation is always a little bit behind. But if you use this approach, you define your API first, and then later you implement it, meaning that your documentation is always up to date. And even better, if your API changes and you update the version of your API, you can actually leverage your compiler in warning you that something has changed. So for instance, if you add new methods, then your compiler will warn you saying that you have not yet implemented these new methods. Or when on your user data interface, you actually add data or you change data. For instance, your name now has been split in first name and last name. You will actually get a compiler error saying that you you are not actually adhering to the API. So I think this is a really simple, low-level, contract-based implementation um, uh, of using interfaces the same way we would use interfaces in a object-oriented approach, but then with something that lives outside of our code. Now, how do we generate a Swagger JSON? Well, there is a plugin for that actually reads your Spring annotations and maybe some more Swagger annotations, and with that you can indeed generate a Swagger JSON like this, where you have your API definition. Now that's really nice because there is an Open API Generator project on GitHub that actually takes a Swagger definition, and with the Open API Generator, you can then configure a Maven plugin and actually generate a driver. So now, not only when you're implementing an interface on the producer side of the interface, you can then actually on the upstream service use that same API, but now if you notice a class instead of an interface, you can use the generated driver, and then indeed based on that interface use the same definitions that were created. So then as an example, you can just extend the user API, configure that to use the correct host and port, and then you're good to go, because all the methods that are there on the API definition can now be used in code on the other side of the interface. So this means that on both sides, the compiler can actually help check whether or not your interface is correct and whether or not you can indeed get the data that you want. And this was actually really nice. We used this in my previous engagement to great effect, because we were always keen on API changes. So in this way, we've actually firstly defined the API, and we are actually also leveraging the fact that we have defined this API not just in Swagger JSON, because that could also be the case, but also generated the Swagger JSON from code, but only from a really thin interface layer that we can then implement in for instance, service B. And then service A can actually generate a driver itself based on the Swagger JSON on that version of the API, and then use it in service A. And the nice thing of course, of doing this is you don't actually need to generate a driver if you don't want to. You could still, if you're not in Java or not in Kotlin or in some other language that it might have a weird definition, or you just don't want to have the dependencies that are generated by this driver, you can of course also just not use it. You can still connect to normally to the API that you're exposing from service B. So in short, if you have a downstream service and an upstream service, you can generate Java interface. You can define Java interfaces, generate the immutable classes and a Swagger file, and later a driver, and then implement those interfaces using the immutable classes. And on the other side, use that driver to communicate between the two. So this, of course, all happens outside of your actual services, but it is a really nice pattern, I think, to leverage the compilers of these separate services to make sure that you actually have the correct data and the correct typing. So it is nice that you can indeed define an interface, but of course you need to exchange information across this interface. So maybe there are some other patterns that we can use inside the service to leverage that as well. Because if we consider the service, then maybe from a GUI where a user types in his or her birthday, maybe we want to collect that as year, month, day, because then we know in 3 integers what the birthday is. But maybe inside our service, when we consume that information, we might want to reason about a local date, that we have a date object that is indeed something that we can reason about way better, because maybe we want to take the difference between two local dates, and the local date object is very well equipped to do that. But then if we want to store that in a database, for instance, we might want to store it as a string. And if we then want to internalize that string, we need to map it to a local date again. And then if we want to expose it to a user, we might want to communicate an age that is in a completely different data type. And in this way, I think it's nice to have a shared language on how you take and expose data across an interface. So, for instance, I would propose that we talk about potential users that we consume, and we externalize users, or we internalize an external user, and then we expose a user. Because once you do that, then the only thing that you're actually interested about is the data of your user in your service. And that's, of course, where you actually want to implement your business logic. So to explore this further, let's consider a service, and in this case, the actual service class. So now we are actually in a microservice where we want to implement some business logic. So indeed, we can see that there is some get users that the controller can call, and maybe there is an adapter where we indeed can get users from a database. But notice that in here, we only actually are considering the user that we ourselves have defined that exists inside this microservice. So it becomes really easy, and even with, or more so even with Kotlin, we can define, for instance, extension methods to say, okay, we are a business that maybe wants to sell alcohol in our web shop, but we need to implement legislation based on different regions, because in the US you need to be 21 to consume alcohol, and in the EU it might be 18, or in other regions it might be even different. So the business rules are, you can only sell alcohol to people that are old enough to drink. And then, of course, you can define these kinds of business rules where you can say, okay, let's get the users that are old enough to drink in the EU or the US, and then you can filter on the age, and the age is indeed a period between the birthday and a local date now in years. So I think this shows that you want a birthday in a certain format, for instance, in this case, local date, because you can then use that data structure to easily implement your business rules. So I would think of a service and the data that flows through this service. What is the best way of implementing business rules on my data and on my data structure? And that should be the problem that you are actually solving in your microservice. And then, of course, you are not bothered by what form your data is on the other side of your interfaces. So let's then indeed build a user, a data model specifically for this purpose. And of course, if you are in Kotlin, then we are already done, because we want a data class of type user with a name and a birthday. And this is all we need to actually apply our business rules. Now, of course, we have to communicate with this data across interfaces. So if we have indeed our shared language of how to transform this data from our user into our service, and maybe from a database into our service, we can actually reflect that on the data. Because I think that the data that you have and the data that you map it to is actually the same data, just in a different format. So if we have our shared language, then we can just define an extension function on our potential user, and then map the name, year, month, day like this into our user data class. Now, of course, if you are an OO purist, then you would say, hey, this is tightly coupling something in the constructor. You shouldn't do this. And then, of course, you could be right, and then you would do this in a converter. But of course, what I like about this is that you actually show that the data that you're using is tightly coupled because you have a mapping here and you want to map a potential user to an internal representation of your user. And this worked actually very nicely in my previous engagement. But having said that, of course, if you want to be more traditional in this and make converters, that's also, of course, fine. Then the other way around, you might want to expose this user back to the front end or upstream, and then you can just implement, here's that word again, interface. So if we make this user data structure exposable, and then we'll come back to that later why this might be handy, then we can just implement that here as well. And we can implement a function expose where we indeed map it from our internal representation to our exposed user. And of course, our exposed user, and with Kotlin, we can use type aliasing, which is really, really nice. This is just the generated immutable class that we generated earlier. Okay, once we have defined that, we have actually defined with shared language how to map a potential user to our internal user and how to expose our user to the outside world. And then if we then look back at our controller, we can actually do this. So if we have a service and we get a user list, then we can map over that list and expose all the users. Meaning that this extension functions actually always exposes the user to the correct data structure that we want to have outside. And this we can do, of course, for all the methods. And remember that we have implemented an interface called exposable. And if we do this, when we make an extension method on exposable and list of exposable, then of course we can just even write this shorter, where a controller now no longer does anything other than calling some service and creating a response, which is of course exactly what a controller should do. So if we then look at this post mapping, it actually becomes more like prose, that you can actually read in English that you get a user, you consume that user data, you let the service save it, and then you respond back to the upstream service, which I think is rather nice to actually have that in your code. It does exactly that. And this is because we have defined share or common language on the interface that is implemented here at the controller. Now, of course, we also need to do the other way. So the other side, the South Pole side, if you will, or the backend side. And of course, if you just implement another interface called externalizable, then you can have a function that uses the shared language on the other side as well, that is called externalize, and then use the models that we have in our driver to actually externalize it back to the backend. And of course, if we want to get something from the database, we can use the internalize function as well. And for that, we need a constructor. So in this case, I think the nice thing of this approach is that you are actually thinking of the data in a way that is exposable, internalizable, externalizable, and consumable. So this is the other part of that interface. Now, just as a side note, if you think, okay, it's nice that you have this user, but it's a flat data structure. Of course, we can extend this with more nested objects. So just like the magnet, the bar where I started with in the beginning, this is a pattern that can drill down to other objects as well. If I have, for instance, an external user, and I internalize this, then all my metadata or other objects, I can then still use the same pattern because we have this shared language, so we can internalize those structures as well. And this is then a data class example of the metadata, where we just define in the same way this relation. So then looking back to our services, what we have defined now are the interfaces here, how we can indeed leverage the compiler to make sure that this side knows what this side needs to know with Swagger JSON, a driver, and an interface implementation. And we have defined a way to map all this data. So if we would split that out, this would, I think, if you look at the microservices architecture, then your microservice architecture should be nothing more than a network of data and functions that map one piece of this data to another piece of data. So all your internalize and expose, externalize and consume functions are the same everywhere. And your tightly coupledness or your mapping is indeed on the data. And then when you look at your services, then this is just a collection of pipes that might not have anything to do with each other, because this is just the piece of code that implements your business logic. And in this sense, you can indeed work on your service in isolation. And then when you make this picture complete with your database, it is also apparent where you need to store your state. And that's, of course, in the databases. So that means that all these services should be stateless. Now, there's one interface I did not yet touch. And of course, maybe I shouldn't call this front-end to back-end interface, but it is basically where the GUI or the HTML or the browser part of your front-end lives. We have talked about interface between services and with an ORM or other drivers, maybe two databases, but not yet how we can leverage this in the front end. And then, I mean, the actual front end in the browser. So I would like to talk a little bit about that as well. And for that, we at Flock, we have created GraphQL simple bindings, which well, it looks like it's about GraphQL, and yes, it is only actually the schemas of GraphQL. I would like to focus more on the simple part of this. So it is also a Maven plugin that you can just use and find on GitHub. And what we can do with that is configure the plugin to generate based on GraphQL schemas to generate Kotlin and TypeScript data classes and interfaces. So as an example, if we, for instance, have a user that implements a person interface, then we can model it like this in GraphQL schemas. So this is actually a GraphQL schema. And we used this not because we needed to implement a GraphQL layer, for instance, but if we just hijack these GraphQL schemas, then we can also use the the tools available to check whether or not these schemas are correct. And maybe later on, if we actually do want to have a GraphQL layer, we can also just reuse these schemas. But for now, it is if we go back to when you would maybe need this, is when you are, for instance, in a small hobby project, or maybe even in a startup, or when you have a small team, then you might not have a microservices architecture yet, and you still would want to have some compiler bindings between your front end and your back end. But of course, if you are working with a microservices architecture, you could still use this. I'm just mentioning it because, of course, if you have Swagger JSON documentation, then there might also be all kinds of tools out there that actually just read from the Swagger JSON and generate your TypeScript interfaces. But anyway, if you want to focus on the simple part of the simple bindings, you can just define your data. And then when you generate it, you will actually have generated a TypeScript interface. And in this way, you can leverage the TypeScript compiler to actually check your types. Moreover, you can just use this in your package.json, you can just point to where these bindings were generated, and you can, because there is a package.json in there as well, you can use it like this in your code. So as an example, here you have your GraphQL simple bindings, your user, and then of course you can apply the same pattern. You can import this user as an external user, and then you can define an internalize function where you can indeed map your external user to an internal user. And then you can just fetch some API data and internalize it. So I think if you use this here as well, you are actually propagating the same shared language, not only in your services but also in your front end, and you know exactly what direction this data is flowing into. It is coming from an API into your system, and of course you can do this all the way around as well. Now the nice thing of TypeScript is actually you don't need to use TypeScript as a language. So if you're using just plain JavaScript, for whatever reason, might be a reason that you do not like build steps in your pipeline. For instance, where I'm working right now, the philosophy is that you want to do buildless JavaScript development, and then of course you cannot use TypeScript in a build step per se, but the TypeScript compiler can actually read these annotations and these comments. So if you want to define your types like this, you can indeed still import user schemas from a TypeScript definition file and then use it in the same way as before. And I think that's really nice that you can use the same patterns as well in JavaScript. Now, of course, on the other side, we also need to have these things generated, because otherwise we would be able to just expose anything to the front end. We do not want that. So on the server side part, we can indeed use the generated data classes and use that to feed the front end. So then again, we can actually apply the same pattern where we have a backend and a front end, but now in between we have a definition with GraphQL schemas where we can just generate Kotlin classes and TypeScript interfaces, and we can use those data classes in the backend and the TypeScript interface in the front end, and thereby leverage the compiler to actually communicate between the two. So just to summarize what we have been talking about, I think as teams and organizations and systems grow, then there is not only a need to organize your code internally as in your application, but also to organize your interfaces externally, where you can define how your systems communicate. And even better, it might be that you are an architect, and if you have defined your interfaces everywhere, you might even be able to just create a pull request to one of these interfaces, and then your teams can accept that and implement it. So it might be a really nice way of testing whether or not your architecture is built in the way you originally thought it should be. Then the patterns I described is indeed define a service-to-service interface and use that compile time with Swagger and driver generation. Then, of course, try and evolve a language to describe interactions across interfaces and use that compile time to your advantage. And then define models that can be used on the front end and the back end, and use your compiler to check that. So in short, leverage your compiler. And with that, I have one last slide, because I think it amounts all to how robust your code is. And of course, I think we know all this testing pyramid where you have end-to-end tests, integration tests, and unit tests. But I think this picture is incomplete. And I think we also need to add our compile time tests, where we use our compiler to test whether or not our code is actually doing what we think it should be. And with that, I thank you. And maybe there are any questions. Yeah, Govert?
Oh, yeah, Govert has. Please.
Yeah, so I was wondering, maybe it's just a Java thing that I don't know, but the pattern that you were discussing, where you have like an object representation, so you have like a class. In this case, it was the birthday, I think,
Hmm.
um, and you have different representations of that object. So you have some version that is used in the front end, some in your database, and then you want to be able to construct these objects and export them. Uh, and you defined, yeah, these internalized and externalized names. Um, I've seen this pattern sort of before, but in a more abstract way. So that you would have like a class which is birthday, for example, but instead of constructors, I mean, that's just an implementation detail, I guess. But on the class itself, you would have a from and then a type. So you can like from, um, let's say yeah, type could you have like a from string or like from UTF date string, for example, or
Yeah.
um, and then with an argument, and then it would construct an object of that type, and every object would have like a to function that would create an object of the type that you want. So instead of having like considering the class as a thing with a pipe with like one input and output, it's more of a generic thing that you can construct from multiple types and that you can yeah serialize into multiple different types. Um, do you feel like that's a more generic way of thinking of the same pattern, or like how would you?
Yeah,
Um,
I think what so of course if you do one-to-one mapping only, then that might be something that you can generalize, and there probably are libraries out there that do that, and then you can construct it that way. But if you are certain that there is indeed only one-to-one mapping, then you can just use the objects that there are in the that you get from the database, for instance, or something else. But there could of course also be, and in my previous engagement I actually saw that, is that you are combining uh, different data structures into one, or splitting them, or
Mhm.
maybe already do some mapping logic that if there are if your age is above 18, then maybe set a boolean, or there could be all kinds of things that you want to do in these mappers. And of course then that might be not generalizable with these to and from uh, generic approaches. And then of course you would resort to writing your own mappers, and maybe doing it in this way. So this is, I guess, more generalizable anyway, because you're mapping these things manually.
Mhm.
But what I also really like is that you are in control of the mapping, and that the compiler actually breaks when you do this. So because you are defining these mappers, if then a downstream service uh, splits, or no, maybe an upstream service splits a name into a last name and first name, then maybe your generic approach might only consider the first name because that was a string or something. I don't know. Of course, it depends on the generic implementation, and we should then look into the specifics of these mappings. But it could be, of course, if you do that automatically, then and serialize something that is a string, then yeah, this would be done incorrectly. So yeah, in short, to answer your question specifically, then of course we would need to look at the actual use case. But what I like about this approach is that you're actually being told by the compiler that something changed, and then of course that will happen more often in a larger organization where data um, is changed in a way that you're not aware.
Yeah, no, I think you slightly must have misunderstood my question. So I don't mean necessarily having generic to and from functions that you can apply to every data object. You still
Mm-hmm.
have to create your own custom.
Okay.
Like mapper functions. But what I mean, so for example, in your flow, you have one specific externalize and one internalize, and you say that okay, if we change the contract from the external part, then we change the signature of the externalize function, and then you will see that things will break. But what I mean is that the model doesn't necessarily have one consumer and one like on every side, if you understand
Right.
what I mean.
Yeah, true. So
Model
if there
itself
would
can have
be
multiple interfaces. So if
Yeah.
you would like to change the internalized signature,
Yeah.
you can have a from date string and from first name last name or whatever,
Yeah.
and you can have different. So instead of changing the signature you have, you just add additional ways to create this object. And then the consumers can migrate at their own pace, so they can change. Like, one consumer can still use the old interface, and another one can use the new interface, for example.
Yeah, but who would be these consumers? Because in this case, it would be
anyone who uses the interface. So because you have this service, and you have like people who call your service, and you have things that your other services that you're calling. And if you have only one internalize, I think that was the name you used for the calling service side, and you change the signature of that, you require that all your consumers all change in lockstep with your signature change. But if
so
I think one maybe specific example could be like say you have a user, and one way is to internalize a GitLab user, and other way is to internalize a GitHub user, or something that you have two different sources of possible users, but you want to internalize it in one way.
Yeah,
for example, one internalized method would not be enough in that case. That's what you mean?
True. So then you could of course just overload that consume method, and you can have an extension method on a GitLab user and on on an Azure DevOps user or something, and then construct it indeed differently. So you would need to create internalizers for every type of user that you want to map to your internal object. That's true.
Yeah. So of course in Java you have overloads, which makes sure you don't have to use many. Yeah, in JavaScript you couldn't do that, of course, because we don't have overloads there. But I guess it's
for instance, here, external user internalize, you could of course just have another external user dot internalize, or if this is a GitLab user, then this is indeed an external GitLab user dot internalize and an external DevOps user internalize, and then you have to indeed define the map between those two data types.
Yeah. I guess because Java has, you can overload, like you can have multiple function signatures with the same name with different types. And that allows you to have like, so you can have multiple constructors, whereas that I'm used to that for every, but it's essentially the same thing. So
and of course a constructor is just another method. So you could just create functions that does that.
Yeah, exactly. So instead of the constructor that takes an external user, I would see like a function from external user that takes an external user.
Yeah, exactly.
And creates an object. Yeah, okay, so it's more or less the same. Yeah, so I was wondering how. Yeah.
Actually, I have to say, in TypeScript, I do use the pattern that Gaffer says. I always say that from blah 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 from.
Yeah, exactly.
Because
so in the end, of course, the point is that if you have a shared language on how to do this, then you know what directions these data objects come from, and also to create a buffer and really map close to the border, so close to the interface, so that your internal your service internals and actually where you do your business logic are protected, so that you do not have to change everything immediately, but only in that converter or mapper or constructor or wherever you want to do the mapping between those two objects. And in this case, it's just nice in Kotlin that you can indeed implement an exposable interface and use extension methods to create a more expressive language to actually do that and reflect it in the language that you're using.
I do think that what you cannot do is, for example, like say you have 3 different versions of your API, and then you would need an expose version 1, expose version 2, expose version
Not
3.
necessarily.
Because you cannot overload
the
return type.
No, that's true. So it could be, of course, that you would then just implement another controller where your expose function is indeed something else. So then expose or I don't know. You could implement a deprecated exposer or an interface that says I'm a deprecated exposable or something else, just to make sure that indeed this is an old version that is going to be deprecated.
Yeah, exactly.
And then you can also remove that.
Yeah, thanks, Jerre, for this really cool presentation. Yeah, and then thanks also for the really cool slides. For me, it, like I already can say, for me it was very cool to see the visuals with this as well, because it's a very abstract topic you talked about, and have these visuals support you, and that was was very helpful for me. So that's a plus here. And
Thanks.
I don't have any questions just because of that nice imagery.